Hello friends, good afternoon and welcome to EduSet Live Lectures. Dear friends, today in Science and Physics we will talk about Special Theory of Relativity. To discuss this topic we have with us our subject expert Dr. Sonia Bansal. Dr. Bansal is Assistant Professor in YMCA University of Science and Technology, Faridabad. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you. Today's lecture is the special theory of relativity. What is the meaning of special theory of relativity? Relativity, when we talk about the relation between the two frames. Then what was the concept? In 1970, Albert Michelson performed an experiment which was the Michelson-Morley Experiment, where he performed it in the two direction, and he found that there was no displacement of the interference fringes. As we know that Michelson found out the interference fringes and there is no displacement of the interference fringes, so that the result of the experiment was negative, and therefore show that there is still a difficulty in the theory itself. It means what was concept was given was not accepted by the Albert Michelson. Then first we talk about the classical relativity. First we talk about the relativity in the classical terms, means we talk about the era of the Newton. What was the assumption that time? That time it is assumed that the Newton's law of motion must be measured with respect to or with relative to some reference frame. It means when we talk about any point or any body, then we define that body with respect to any coordinate or any frame should be there, so that we can define the body's physical significance and all the parameters with respect to any frame. Then Albert Einstein surprised the world in 1905. What he was said that the time and distance cannot be measured absolutely. It means it's not a fixed, it may be change. The second, he told that they only have meaning when they are measured relative to something, means all the values will be changed if we take the relation of the time and distance with the other things. Means Einstein published his theory in the two steps. In the first step in 1905, where he defined the special theory of relativity, where he defined that how space and time are interwoven. And in the second, he defined the general theory of relativity in 1915, effect of gravity on space and time. Then what is the word relative in the relativity? Relative means, as we talk about that time and distance is not measured absolutely, they are measured relative to something. It means if we talk about the motion, time and distance define the motion. Then if we talk about the motion, then all motion is also relative to each other. Measurement of motion means we are measurement of the space and time. Make no sense unless we are told what they are being measured relative to each other. Then first we talk about the relative in the relativity. Then what is the absolute in relativity? Absolute relativity means the laws of nature are the same for everyone. Time is same for the everyone, and second, the speed of light in a vacuum c is the same for everyone. The value will not change at any cost. It will be same for everyone. That is the absolute in relativity. Next, what is relative? Here we are having an example. Here a plane flies from the Niobe to Quito at 1650 km per hour. The earth rotates at the equator at 1650 km per hour. If we talk about an observer, then on the earth's surface sees the plane fly westward overhead. At a far distance, if we see that the plane stand still and the earth rotate underneath it, means for the one observer can see that the earth is moving, the another observer sees that the plane is moving. Then both the things depend upon the observer. Next, in 1905, Albert Einstein changed our perception of the world forever. He published the paper on the electrodynamics of the moving bodies. In this, he presented which is called the Special Theory of Relativity. It was published in 1905 on the page number 891 to 921, and journal was Analytical Physics 17. What he discussed about that, what was the background of this work, what was the new idea that he proposed, what was this experiment confirmed, how does this influence our thinking today, what was the concept of. In that paper he defined the theory of relativity, but the basic aim was to define the special theory of relativity. The law of physics are known to be unchanged. It will be invariant under the rotation. If we talk about any rotation, then the physics law will be the same. A rotation mixes the space coordinates but does not change the length of any object. The length will be the same, the body is moving, but the length will be the same. So it is the linear transformation. He defined the linear transformation. In the next concept, he defined the spatial relativity extends into this invariance for certain transformation of space and time together. He considered the space coordinates means x, y, z as well as the time t into a 4-component vectors. Means if we define any body in any space or in any reference, that it will be defined by the space coordinates as well as the time coordinates. Means we define any body by the 4-component vectors which are x, y, z and time t. Here c is the speed of light. According to relativity, it is the same in every reference frame. Its value will not change. If the frame of reference will change, but the value of c will not change. In the other concept, he defined the relativity states that all laws of physics are invariant under those linear transformation. Which was it? It means x1 approaches to summation j is equal to 1 to 4 defined for the coordinates m, I, j, x, j, which leaves x square plus y square plus z square minus c square t square. It will be unchanged. All will be same in the all frames. This quantity is like in the length in space time rather than just a space. Means here we are not considering only the space coordinate, means we are not considering only the x, y, z coordinate, but we have to take the time coordinates also to define any body, and it will be unchanged. We now examine the physical meaning of this statement as well as how it came to be proposed by the Einstein, that we will define here. Before that, we define that what is the electrodynamics behind it. The crisis that motivated Einstein's works was related to the laws of electricity and magnetism, that is known as the electrodynamics, where he defined the 4 laws. We all know about these 4 Maxwell laws. These laws were known as the Maxwell law and embodied in his famous equation. This equation, del D is equal to 4 pi rho, del cross H is equal to 4 pi by C j plus 1 by C del D by del T, del cross E plus 1 by C del B by del T is equal to 0, and last one is del dot B is equal to 0. These 4 equations given for the electricity as well as the magnetism, and these equations are known as the Maxwell equations. These equations depend upon the speed of light. In what frame in this speed to be measured? The question was that we are defining this speed c, but how we measure this speed c, and in which frame we are measuring the speed of light. It was thought that the light propagates via a medium, means light only pass through a medium. That medium is known as the ether, much as sound waves propagates via air and or water. Means if we pass the light, then we require a medium, and that medium is known as the ether, and it compared it with the sound wave that is propagated in air and water. So, it means the light wave will pass only through the medium, that is the ether. In that case, the speed of light should change when we move with respect to the ether, just as for the sound in the air. The speed of light will change as the ether move. The light speed will be moved accordingly with the speed of ether. That was the concept. So, c would be the speed of light as measured while one is at rest relative to ether. Then speed of light will be calculated for in the two frames, one is at rest and second is moving, that must be relative to each other. Here what is a reference frame? Previously we defined that relative to each other, that we define in the reference frame. Then what is a reference frame? Two or more objects which do not move relative to each other share the same reference frame. They experience time and measure distance and mass in the same way. Objects reference frame means we are considering the two frame, one is at rest and other is moving. Objects moving relative to other are in the different reference frames. As we are having an example, just we see the plane is moving. The passenger in the plane is static. The plane is moving, and on the ground the observer is looking that plane is moving, but for the passenger it is static. Like the plane and ground below. Here we consider the objects moving relative to each other are in different reference plane. Like the plane and ground below, they experience time and measure distance and mass in different way. Here we see the plane passengers see the ball moving 10 km per hour, that is a 10 km per hour, and the plane is moving with the 900 km per hour. The observer on the ground see the ball is moving with 910 km per hour, but the passenger in the plane will see that ball is moving only with the 10 kilometers per hour. It means both are relative to these two can be relate. Plane passengers see the light traveling at the speed of light c. If we replace this with the speed of light c, that is done 10 km, it means for the observer on the ground and for the observer which is in the plane will be different. Observers on the ground also see the light traveling at the speed of light c. The plane passengers see the light traveling at the speed of light c. It means for both the passenger the speed of light is same, but here the speed of the ball will be different. It means we define that the value of c will not change with the frame or with the relative motion. Since the ground observer see light moves at c, the plane passenger is always slower. What is inertial reference frame? Here we define the two type of frame. First is inertial reference frame and second is the non-inertial frame. What is the inertial frame? A reference frame is called the inertial frame. If the Newton's law are valid in that frame, only that frame is the reference plane when all the Newton's law are valid. Such a frame is established when a body not subjected to the net external forces is observed to move in a rectilinear motion at a constant velocity. All the body is moving here with the constant velocity. Newton's principle of relativity. If Newton's law are valid in one reference frame, then they are also valid in another reference frame moving at a uniform velocity relative to the first system. All law will be valid. In the next, this is referred to as the Newtonian principle of relativity, or that is known as the Galilean invariance. For this, here we define the inertial frame. Inertial frames, we consider the two inertial frame K and K dash. We already defined that any body defined by the coordinates x, y, z coordinates. Here we consider the two reference frame. First reference frame is K and second is K dash. The frame K dash is moving with the velocity v, and here this frame K, which is defining the coordinate x, y and z is the static, but this frame k dash having the coordinates x dash, y dash and z dash and o dash is the center is moving with the velocity v. K is at rest and k dash is moving with the velocity v. Axes are parallel for the two reference planes. K and k dash are said to be in inertial coordinates system. Here we define by the x, y, z and x dash, y, z and z dash, and time period defined by the t and t dash. Now we talk about the Galilean transformation. As we talk about that, if we have any particle or any object which is defined by the p. Here we two references k and this is the k dash. This k dash is moving with the velocity v and this is the static plane which is the k. Now this is moving along the x axis. The frame of reference is moving, frame of reference k dash is moving along the x axis with the velocity v. This is the v. Then in the system k, if we talk about the p, then what are the coordinates of p? It will be, for this frame, the coordinates of p is x, y, z and t. We talk about that, already talk about that, the system defined by the 4 dimensions x, y, z and the time t. So now here the point p for the reference k which is static reference and having the coordinate x, y, z and having the time coordinate t is defined by the x, y, z and t. In the system k dash which is moving with the speed x dash, then it is defined by the x dash, y dash, z dash and t dash. Here we see that if we talk about the x dash, the value of x dash is equal to, with respect to this frame, the value of x dash is equal to x minus vt. Means x dash is moving with respect to frame k and the value of x coordinate for the moving frame will change by x minus vt. Condition of the Galilean transformation. Here we define the parallel axis, the frames are moving parallelly and k dash has a constant relative velocity in the x direction with respect to the k. So the coordinate x dash is converted into the x minus vt and y dash converted into the y and z dash is equal to z and t dash is equal to t, because these planes all are parallel to each other. The time t for all observers is a fundamental invariant that is the same for all inertial observers. The t value will not change and the axis in which the frame is not moving will not change, only in the axis in which the frame is moving will be changed. The inverse relation, if we talk about, it means if the velocity is replaced by the minus v, means if the frame is moving opposite to the opposite direction with the velocity minus v, then replaced primed quantities with the unprimed and unprimed with the primed. Then we define as x is equal to, it will be x dash plus vt, y is equal to y dash. As it is moving along the x-axis, then this value will change only, otherwise all are parallel to each other. That is, it will be y is equal to y dash, z is equal to z dash and t is equal to t dash. The transition of the modern relativity. Although Newton's law of motion had the same form under the Galilean transformation, Maxwell equations did not. In 1905, Albert Einstein proposed a fundamental connection between the space and time, and that Newton's law or only an approximation. Means the Newton's law is not valid, but here just given the relation between the or the connection between the space and time. Then for defining this, they required a medium, that is the ether. The wave nature of the light suggested that there existed a propagation medium, and that is called the luminiferous ether, or just is known as the ether, which is a massless, which is a transparent material. That most of the points has been defined for this ether. Ether had to have such a low density that the planets could move through it without loss of energy. the other concept, it also had to have an elasticity to support the high velocity of light waves, and this is the medium to pass the light. Then Maxwell equations define as, in the Maxwell theory, the speed of light in terms of permittivity and permeability of the free space we have given by V is equal to C, and which is equal to 1 by mu naught or epsilon naught. Mu naught is the permittivity and epsilon is the permeability, means we define for the electricity as well as magnetism. Thus, the velocity of light between the moving system must be constant. We will not change, and it will be the constant, which is equal to the speed of light, which is c. An absolute reference frame, the ether was proposed as an absolute reference system in which the speed of light was this constant and from which other measurement could be made. Absolute reference frame which will not change, it will be the static. It means ether is defined as the absolute reference system, and the speed of light will be defined in reference to the ether. The Michelson-Morley experiment was an attempt to show the existence of ether. If ether is present in the atmosphere and it is moving with the speed of light v, it means the experiment is also moving with the speed of light v. The Michelson-Morley experiment, what was the Michelson-Morley experiment, and when it was defined, Albert Michelson from the 1852 and 1931, and in 1907 he got the Nobel Prize to define his experiment and build an extremely precise device which is called the interferometer, which defined the interference pattern to measure the minute phase difference between the two light waves travelling in mutually orthogonal direction, and it defined the wave nature of the light also. What was the experiment? This was an experiment designed by the Michelson, and where we defined the mirrors, microscope, light, initial light beam, then light beam is passing through it, light beam viewed in the microscope, semi-silvered mirrors are used, adjustable mirrors are used, glass plates used to balance effect of the refraction, other light parts, one light path mirrors are used, and adjustment of this experiment, then the interference pattern is received. Then experiment were performed to compare the speed of light when is moving along or against the ether. This experiment was performed along the ether and opposite to the ether, means first it was defined at the 0 degree relative to the ether, and in the next step it was done for the 90 degree also. Using the traditional mechanics, it follows that the transit time r, when we define the transit time for this experiment, it will be t, which is moving along the ether, defined by the t, which is equal to 2L by c, 1 minus v square by c square. When it is defined perpendicular to it, its value is 2L by c root of 1 minus v square by c square. So, there should be an observer discrepancy. This is the experiment, Michelson Interferometer, that we also define interference, but this is for the theory of relativity. Here we define the monochromatic source of light. This is the slit, light pass from this hole and fall upon the partially silvered mirror, which is inclined at 45 degree angle, and here there is a compensator mirror, light pass from it, means light is refracted here and light is reflected here. The light reflected having the double path as compared to the light refracted. So, this compensating plate is introduced between the path of the refracted ray, and this is the mirror 1, this is the mirror 2, and this is the optical path, this length is L2 and optical path length is L1, and this is the eyepiece where the interference pattern will be observed. Light coming from the source, pass from the slit, then reflection and refraction takes place from this partially silvered mirror, and through this mirror M1 and M2 we get the interference pattern. These two mirrors should be parallel to each other, means these two mirrors should be perpendicular to each other, but the image of mirror M1 should be parallel to the mirror M2, means image of M1 should be parallel to the mirror M2, but in general this mirror perpendicular to this mirror. Now this apparatus is moving with the velocity v. This is the ether shift. It means this experiment is done in the presence of a material which is called as a ether and which is moving with the velocity v, and the length of refracted ray is L1 and the optical path length of the ray which is reflected is L2. This is the original experiment. The original experiment compared with the back and forth travel time of the light parallel and perpendicular to the supposed ether. Here we just define an experiment, and by using this I just show that how this is working. Here we consider that this is the length, a fixed length is defined here, and a material is moving with the velocity v, and that material is the ether. And now we start from this point, and the distance of this point and distance of this point is the same. Now if the ray is moving from this direction and moving perpendicular and moving along, then the difference between these two, that the ray which is going to upside, means going perpendicular, will not go the straight. First it will go diagonally, then automatically it reach this point. It will take the path C and it will take the path V, but the ray which is going towards along the ether will take the path C plus V, and if it moving in the opposite direction it will take C minus V. And on the basis of Michelson Interferometer define, where AC is the parallel, here if we define this diagram, then we find out that AC is parallel to the motion of the earth including an ether wind. Means this path, this optical path is moving with the ether drift which is moving with the earth, and light from the source S is split by the mirror A and travel to the mirrors C and D in mutually perpendicular direction. Means from this glass plate which is partially silvered, the path is along the D and path is along the C, which are mutually perpendicular to each other. After reflection, the beam recombined at A. Again there is a reflection and it will come at the point A slightly out of the phase due to the ether wind as viewed by the E, and these two rays are in phase and produce the interference pattern in the microscope, and then we can see that this experiment is done in presence of the ether, and it is defined that ether is present in the atmosphere. Then we will back after the 2 minutes. Thank you. Welcome back. We are defining the Michelson Interferometer, and this is defined along the direction of the ether as the earth is moving along the direction of ether, and this experiment is done along the direction of the ether. Now this experiment has been done at 90 degree also. That is defined as that the typical interferometer fringes pattern expected when the system is rotated by the 90 degree, and this is the diagram where we see that here we have the different fringes. One is high intensity and one is low intensity, means we are having a constructive and destructive interference which define the interference pattern. In this interference pattern, we define that if the interferometer is moving along the velocity v, then the fringe should be shift from one place to the another place, but it was not done. Then there is a negative result of this experiment, and this experiment was performed and the two ways along the ether and at 90 degree also. Then what was analysis has been done, then assuming the Galilean transformation, then we define the time t for the light which is moving along A to C, which is the reflected light, and then we find out that time t is equal to 1 L1 for going this side, and then it will come back, then again L1 which is moving along the velocity v, then it is c plus v. When it is coming back along this side, then we define as L1 divided by c minus v, and then it is 2cl1 by c square minus v square, and which is equal to 2l1 by c. We will take the c common, then we define it as 1 by 2l1 c 1 by 1 minus v square by c square. The time 2t from A to D and back, the one ray which is going towards this and second ray which is reflected, which is going towards the D, which is going to the mirror M2, and it is coming back from here to at this glass plate which is A. Then the time period we define as T2 is equal to 2L2 divided by root of C2 V square. Here we directly written, then one time for going that side and one time coming back. Then it will be equal to 2L2 divided by C, or we can write it as 1 by root of 1 minus V square by C square. And this is here it is not equal to, but this is 2LC into 1 by root of 1 minus V square by C square. Now, so that the change in the time is defined as the delta t is equal to T2 minus T1. What is the time difference between these two rays which is going towards the ether and one is moving perpendicular to the ether? The time period delta t, the change in time period, is equal to 2 by C L2 by root of 1 minus V square by C square minus L1 divided by 1 minus V square by C square. Then upon rotating the apparatus, the optical path length L1 and L2 are interchanged and producing a different change in the time, and that is, note the change in the demonstrators, that is delta t dash is equal to T2 dash minus T1 dash, that is 2 by C L2 by 1 minus V square by C square minus L1 by 1 minus V square by C square. Here we don't have a root term, and here we are having a both the terms here. That is done parallel to the ether, and this experiment done at the 90 degree. Now thus a time difference between rotation is given by delta t dash minus delta t. What is the effect of rotation? Then we are considering here both the time period. One is at a 0 degree along the ether and one is perpendicular, means at 90 degree of the ether. The time difference is defined as 2 by C L1 plus L2 divided by 1 minus V square by C square minus L1 plus L2 divided by 1 minus V square by C square. And upon a binomial expansion, assuming V by C very less than 1, speed of light is more as compared to the speed of the ether, then we define it, this reduces to delta t dash minus delta t approximately equal to V square L1 plus L2 divided by C cube. What was the result of this experiment? Using the Earth's orbital speed as v is equal to 3 into 10 power 4 meter per second, together with L1, L2, if L1, L2 are same, then it is 1.2 meter, so that the time difference becomes delta t dash minus delta. If you consider the above equation, then we have v square L1 plus L2 divided by C cube, which is equal to 8 into 10 to power minus 17 second. Although a very small number, means the difference is very small, it was within the experiment range of the measurement of the light waves. Maybe this may be the error, but this not be considered that fringes shift or the apparatus is moving with the ether. Then what was the conclusion of the Michelson interferometer? Then Michelson noted that he should be able to detect a phase shift of light due to the time difference between the path lengths, but found none. Means there is no shift of the fringe, means it is not moving with the, there is light is not passing from any material. He thus concluded that the hypothesis of the stationary ether must be incorrect. There is no medium required to pass the light. It means ether medium is not present to pass the light. Experiment said. After several repeated and refinement with the assistant Morley which was from the 1893 to 1923, again in null result, he found this experiment was done under many conditions and done repeatedly, but always the null result was found, only the minor error was there. Thus ether does not seem to exist in the atmosphere, and there is not required of any material to pass a light. Then what was the possible explanation of that? Many explanations were proposed, but the most popular was the ether drag hypothesis, the negation of the ether present in the atmosphere and it is moving with the velocity v. This hypothesis suggested that the ether somehow dragged the ether along as it rotates on its axis and revolve around about the sun. This was contradicted by the stellar aberration, wherein telescopes had to be titled to observe starlight due to the Earth's motion. If ether was dragged alone, this tilted would not exist. Then what was the Lorentz contraction? Another hypothesis proposed independently by the Lorentz and Galilean suggested that the length L1 in the direction of the motion was contracted by the factor of root of 1 by v square by c square. The another concept that if we talking about the no ether present, but the length of the material is changing. If we talk about the frame of reference, that was a hypothesis, means length is changing by the factor 1 minus mu square by c square, thus making the path length equal to account for the zero phase difference. This, however, was an ad hoc assumption that could not be experimentally tested. It means length is not contracted if you consider the two frame of reference. Then Einstein proposes theory. The Albert Einstein was only 2 years old when the Michelson reported his first null measurement for the existence of ether. At the age of 16, Einstein began thinking about the form of Maxwell equations in the moving inertial systems. Then at the age of 26 and in the year 1905, he published his sterling proposal about the principle of relativity, which he believed to be fundamental. What he proposed? He proposes the two postulates. With the belief that Maxwell equation must be valid in all inertial frames, Einstein proposes the following postulate. First postulate was the principle of relativity. What does it mean? The laws of physics are the same in all inertial frame. Either it is static or it is moving. There is no way to detect the absolute motion and no preferred inertial system exists. The second was the consistency of the speed of light. The speed of light is constant. Observer in all inertial systems measure the same value for the speed of light in the vacuum. The speed of light is same in the vacuum or in any medium. Then re-evolution of the time. In the Newtonian physics, we previously assumed that t is equal to t dash. Thus, with the synchronized clocks, events in k and k dash can be considered simultaneously. But Einstein realized that each system must have its own observer with their own clocks and meter sticks. Thus, event considered simultaneously in the frame k may not be in the k dash. Means simultaneously we can observe the time as well as coordinate for the two references frame, one is moving and one is static. Then here we define a problem of simultaneity. The frame at rest is equidistance from the event A and B. This is the Frank, and which is at equidistance. It is from the +1 meter from here, B is +1 meter and A is the -1 meter. The Frank sees both the flash balls go off simultaneously. He can see that this flash ball will go off simultaneously go off at the same time, and they are at the equal distance. Then a problem of similarity again. Mary moves to the right with the speed v, and this is the moving frame. Previously we defined this is the static frame, but here the observer is moving with the velocity v. Then what will happen? That event B is C quickly, but then the event A, because it is moving along the event B. That is why he can observe this event compared to this event. Now, with this observe, the two events are simultaneously in one reference frame, which is K, are not necessarily simultaneous in another reference frame K dash, moving with respect to the first frame. This suggests that each coordinate system has its own observers with clocks that are synchronized, all reference frame having the different coordinates and different time. Synchronization of the clocks. What are the steps? Step 1. Place observers with the clocks throughout a given system. In the step 2, in that system, bring all the clocks together at one location. Or in the third, we compare the clock reading. If all the clocks agrees, then the clocks are said to be synchronized. Otherwise, they are not synchronized. A method to synchronize. One way is to have one clock at the origin set here at the time t is equal to 0, and the advance each clock by the time d by c. Here is the time d by c, being the distance. D is the distance of the clock from the origin, and t is the speed of light, c is the speed of light. Allow each of these clocks to begin timing when a light signal arrives from the origin. Then what was the difference? Then the spatial set of the linear transformation defined preserve the consistency of the speed of light c between the inertial observers, and the second was account for the problem of simultaneity between these observers. That was defined by the Lorentz Transformation equation. What was the Lorentz transform equation? It means that if the body is moving along the x-axis, means we are considered two frame, one is static, another is moving. Then moving along the x-axis, then the value of x-axis will be changed, and simultaneously the value of t will also change. It means the value of x dash is equal to x minus vt divided by 1 minus v square by c square, but these planes are parallel, then y dash is equal to y, z dash is equal to z, but they are not in moving coordinates, only the x coordinates moving, and hence the time period will change. It will be t minus vx by c square root of 1 minus v square by c square. Hence the Lorentz equation in more symmetric form is defined as, here we define v by c by the beta, and then gamma is defined by 1 by root of 1 by v square by c square. Then x dash can be replaced by gamma x minus beta c t, and y dash is equal to y, z dash is equal to z, and then t dash is equal to gamma 1 minus beta x by c. Properties of y, recall b which is equal to v by c must be less than 1 for all observers, then gamma must be greater than or equal to 1 only when v is equal to 0, speed of light is 0. The graph of b v not equal to c, the value of v is not equal to c, then the graph between the relativistic factor gamma and v by c, means graph between the alpha and beta is defined as that the value of this factor is going to will be static for a while, and it will be increase after some time. Relative factor will change as the time period will change. Now, what was the derivation? Use the fixed system k and the moving system k dash. Consider two system, two reference frame, one is moving and second is the static. Consider the origin, means at t is equal to 0 and axes of both system are coincident with the system k dash moving to the right along the x axis. As we define that this frame k dash is moving, but this is the origin. A flash bulb goes off at the origin when t is equal to 0. According to the postulate 2, the speed of light will be c in both the system, and the wavefront observed in both the system must be spherical. Either it will be moving or it will be static, like this. Then we define the spherical wavefront in k by this equation: x square plus y square plus z square is equal to c square by t square. That is the static frame. The frame which is moving, then the spherical wavefront value will be defined as x dash square plus y dash square plus z dash square is equal to, the value c will be the same in the two frame. Here the value of c is same in the static frame, and value of c is same as in the moving frame, but the time period will change, it will be t dash square. These are not preserved in the classical transformation with x dash is equal to x minus vt, y dash is equal to y, z dash is equal to z, and t is equal to t dash. Now x dash is equal to gamma x minus vt, so that the x axis will be opposite of this, it will be gamma dash x dash plus v dash. Then by Einstein first postulate, gamma dash is equal to gamma, it means both the frames are having the same value. The wavefront along the x dash axis must satisfy x is equal to ct and x dash is equal to ct dash. Thus ct dash is equal to gamma ct minus vt, and ct is equal to gamma ct dash plus vt dash, means define it as a vice versa. Solving the first one above for the t dash and the substituting in the second, then we have the following result, means t dash is equal to gamma square t dash 1 minus v by c 1 plus v by c, from which we derive gamma square is equal to t dash will be cancelled, then we have only the one result, which is 1 by 1 minus v square by c square. Then find out the transformation for the t. Again x dash is equal to gamma x minus vt, then substituting into x is equal to gamma x dash plus vt. Then solving for t dash, we obtain t dash is equal to x by gamma v 1 minus gamma square plus gamma t. Then we can write it as, which may be written in terms of beta is equal to b by c, then T dash is equal to T minus Vx by c square divided by root of 1 minus beta square, means the time period will be changed by this factor of the moving frame comparison to the static frame. Then the complete Lorentz transformation for the moving frame as well as the static frame. These transformation for the static frame and these for the moving frame. This is for the k dash and this is for the frame k. The value of x dash is equal to x minus vt divided by 1 by b square root. Then y dash is equal to y, z dash is equal to z. Then t dash is equal to t minus vx by c square by root of 1 minus beta square. For the static, x is equal to x dash plus vt dash divided by 1 minus beta square. The value of beta is same, means v by c is same. Then y is equal to y dash, z is equal to z dash, and then t is equal to t dash plus vx dash divided by c square root of 1 minus beta square. What was the remark on this? We know that v is very less than c, then beta approaches to 0 and the gamma is equal to 1. We see this equation reduced to the familiar Galilean transformation. It means Lorentz proved the positive result of the Galilean transformation. Space and time are now not separated, they are considering simultaneously. For non-imaginary transformation, the frame velocity cannot exceed c. The value of c will be same. On the basis of that, there were the consequences of the Lorentz transformation, which is the time dilation and the length contraction. The time dilation for the two frames, clocks in x dash run slow with respect to the stationary clocks in k, means the time for the two reference frames will be different. For one it is slow, for two it is fast. Then length contraction, the length of k dash are contracted with respect to the same length stationary in the k. This is the time dilation. To understand the time dilation, the idea of proper time must be understood. The term proper time means T0 is the time difference between the two events occurring at the same position in the system as measured by the clock at that position. This is the time dilation. Here we consider a body which is moving with. The time dilation is defined as not a proper time. Beginning and ending of the event occur at different position. Here we see that the time is not proper. We define it by an example. Here we see the two reference frame. One is static, which is moving along the x direction, and one system is the static. Now coordinates of this, the Frank is at this frame of reference, or here Mary is in this frame of reference and she is the observer. Melinda is the observer. Now what we see, this is the clock time T1. The Frank is in the static frame. The coordinates of this frame is XYZ and he is at the x position. Now he is at the x1 dash position, whereas and this Mary's frame is moving with the velocity v, and he is having the different clock whose time is defined by the t dash, and the Frank having a clock whose time defined by the only the t1. Now this is the observer, x2 dash is the observer. Now this is defined. Now for another time the same will be that it is moving along this direction. Then Frank clock is at the same position in the system K when the sparkles is lit in, and when it goes out, the Mary is in the moving K dash is beside the sparkles at A. Then Melinda then moves into the position where and when the sparkle extinguished at B. Thus the thus the Melinda at the new position measure the time in the system K dash when the sparkle goes out in the B. Means all the observer are measuring the time period in the different concept. They are measuring at the different frames and with the different frames and at the different time and in the different space also. Then according to Mary and Melinda, the Mary and Melinda measure the 2 times for the sparkles to be lit and to go out in the system K dash as the times T1 dash and T2 dash, so that by the Lorentz transformation T2 dash, because it was as x2 dash position and the Mary is x1 dash position. So time period, the difference between the time periods of the 2 observer means Mary and Melinda is T2 dash minus T1 dash, which is equal to T2 minus T1 minus V by C square, x2 minus x1 divided by 1 minus V square by C square. Note here the Frankel records x minus x dash 1, which is equal to 0 in the K with a proper time T naught is equal to T2 minus T1, or we can say T dash is equal to T naught by root of 1 minus V square by C square, and here we define the T1 for the inertial frame, which is equal to gamma T1 with T dash is equal to T2 minus T1. Here means define the moving frame having a time period different as compared to the frame which is at the static. This is the time dilation. Then what was the result? T dash is greater than T naught, or the time measured between the 2 events at different positions is greater than the time between the same event at the one position. That is known as the time dilation. There is a difference between the time. The events do not occur at the same space and the time coordinates in the 2 system. The system K requires 1 clock and K2 dash, which is moving, require the another clocks. Thank you very much.
Dear friends, on that note, we would like to thank Dr. Bansal for coming to our show and delivering this wonderful lecture. With that, we hope that with today's lecture, we were able to understand the special theory of relativity. On that note, thank you, dear friends, for watching our show. Stay tuned and keep watching. Thank you.